welcome to lecture number 24. So, we have discussed about the Kepler's problem for parabola and ellipse or the parabolic and elliptic orbit. The hyperbolic orbit is remaining, but before that we do one more problem, and we have some other issues that I want to discuss. So, let us start with the problem first. So, here the problem is given that prove that earth takes 2 days more than half a year to travel over half of its orbit separated by minor axis away from the sun. So, what is the problem that so, this is the center C, focus is somewhere say here in this point F, and this is your minor axis. So, what it is telling that prove that earth takes 2 days more than half a year to travel over half of its orbit separated by minor axis away from the sun. So, what it is telling in effect that this is half of the orbit, this is the separated by minor axis. So, away from the sun, and the sun is located here. So, you have the sun here in this point, this is sun, okay. And earth is going around in the orbit. Okay. So, away from the sun means we are talking about this area. So, covering, let us say this is A, this is P, and we can write this as A, B, P, and we will write here F and C. So, we will name this as C, and if time taken to cover the area or sweep the area means the suppose the satellite starts from this place and it goes all the way up to here. Okay. So, starting from B and it is going to C. So, let us say that cover the area, this area shown in pink, So, it takes time taken to cover the area, and we will note this area as A 1. Okay. So, cover the area A 1 is T 1, then the time taken to cover the area A 2, this will write as A 2, area A 2, which is nothing but we will show this as F C A B. Cover the area A 2 is, then the time taken is T 2 equal to T 1 plus 2. This is what has to be proved, means 2 days more. So, now I am going to hash this area A 2. So, you can see that in the orange I am hashing this area, and covering this area it takes 2 more days than the pink one. Okay. That means, the sweeping this area by the radius vector it will take 2 more days. This is what we need to prove. So, delta F C A B, this area can be written as area B F C, which is triangle, plus area C A B. Okay. And this area, the triangle area B F C, this will be 1 by 2 this will be equal to 1 by 2 times this base length B C times this distance C f times C f plus where C f is nothing but A e, as we know from our discussion about the ellipse, and B c is nothing but equal to 2 b, and area C A B. So, this is half of the ellipse area. So, 1 by 2 times pi A B, pi A B is the area of the ellipse. Okay. So, all the things are available here. So, if we insert, so this becomes 1 by 2 B C equal to 2 b and C f equal to A e plus 1 by 2 pi A b. So, we have the area if C A B, area F C A B and this becomes 1 by 2, 2 cancels out. So, there is a factor of 2. So, we will remove that and simply we use this see here we have here in this place 2 cancels out. So, A B E plus 1 by 2 pi A B, A B E plus 1 by 2 pi A B. So, now we have to compute. This is the area we have done just now, okay. And let us write this as delta A. So, delta A equal to this is the quantity. Okay. So, and what is this area? This is half of the ellipse, already we have written. So, this area is known to us. Now, time period equation already we know this is 2 pi divided by 2 pi and square root A q by mu under root, and from there we have got the mean angular rate omega to be 2 pi by t equal to mu by A q under root. This is what we have got. So, once we get this mean angular rate, we will be able to solve the problem. Now, also we know that A dot, the rate of sweep of area, this is nothing but h by 2. So, these informations are available to us and we have to solve this problem. So, we have delta A equal to pi A B divided by 2 plus A B E, this is the quantity. Okay. So, divided by, now this omega is the mean angular rate. So, we can also use this information, but already because based on this we have derived this omega. So, directly we can use this omega is a constant, it is a mean angular rate, and rate of sweep of area is a constant. Okay. So, either we directly use this or either we use this, result will be the same. So, therefore, this delta t, this will be pi A B divided by 2 A B E divided by omega. And then we can insert the value here pi by 2 a b, and omega is mu by a q under root. So, this goes as a q by mu under root. Also, see, one thing also we have to note that this time period, this is nothing but pi a b divided by omega. This is the whole area of the ellipse, area of the ellipse, and this is the mean angular rate. Okay. So, omega also can be written as pi a b divided by t. So, where t becomes now the time period. This is the time period of the orbit, time period of the orbit. So, either we can go through this. So, let us go through this route, because this will be little simpler to work with. We can do it fast. So, pi a b divided by 2 plus a b e, and omega we directly put from here. You can see the advantage that a b is already here present in this place here. So, cancellation of the sum of the terms will take place, and that makes our life easy working out this problem. So, this becomes pi by 2 plus a b cancels out, e by pi times t. Pi also cancels out, we divide it by, let us do one more step. We take here t, and then this is pi a b by 2 pi a b plus a b e divided by pi a b. So, this is one more step I have added. So, t times pi a b cancels out, 1 by 2 plus a b cancels out, e by pi. So, this is t by 2 plus t e by pi. So, this is your half year, okay, t by 2, the half of the year t by 2, t is the total period of the orbit. Then what this quantity will be? We have to just insert the value. So, this is your extra delta t. So, the time taken. So, here instead of writing delta t, let us write this as t. So, therefore, this quantity where it appears, this is the extra time delta t. Okay. So, this extra time delta t, then we can write as t equal to 365, E equal to 1 by 60 divided by 1 by pi, and this turns out to be around 1.939, and therefore, delta t is around 2 days, means 2 days extra. It is going to take over half the year to cover the area which is hashed in orange here in this place, which I have shown by A 2, which includes, again I will draw this area, I will mark it by red boundary. This area, you can see this area from here to here to this place. So, this is your A 2, and time taken to this cover this is T 2, and T 2 is nothing but T by 2 plus 2 extra days approximately. So, and rest of the time it will go over this orbit from this place to this place. So, this was a very small problem, but it gives you the concept for working. We have taken this part here, omega equal to 2 pi by t, and also this is the corresponding equation, but equally we could have used this also, and directly we could have worked, and result will be the same. Okay. Once we have done this, now we will get back to the elliptic problem again, and there are some standard integrals available in the books. So, those you can utilize to solve the problem for the ellipse, hyperbola and parabola. So, what we had the problem that it is a given r square theta dot equal to h, and this we wrote as d theta by dt r square. This can be written like this, and this implies dt equal to r square divided by h d theta, and this we integrated from 0 to t, and this side from 0 to theta, or maybe theta 0 to theta, both the integration limit you can put. So, for doing this, then we replaced L r by L by 1 plus e cos theta. So, this whole square, this square, and so therefore, we have written this as, if we start from t here, say the capital T we have written perhaps earlier. So, this gets reduced to L square divided by h d theta by 1 plus e cos theta whole square, and the issue was integrating this. So, we did in terms of eccentric anomaly, and the benefit was that it got reduced into a simpler format, which we called this as the Kepler's equation. So, E minus E sin E. So, from there by integrating we got this equation for the case of ellipse. Okay. Now, integrating this, there are some standard equations available in textbook on integration. So, I will write that, and you can use that also, but this one was more elegant, and it showed finally, because our objective was also getting the Kepler's equation in this format whatever we have written here. Okay. So, the process we followed, it was intentional. Now, the other way of doing the same problem will be, we use this integration, say this is d z alpha plus beta cos z whole square. The integration of this quantity, this will be alpha square minus beta square 3 by 2 alpha tan inverse alpha plus beta under root. Here you need to remember this equation. Okay, that is the difficulty. Therefore, I have not taken that in the beginning. This is z by 2, okay, tan z by 2 minus beta alpha square minus beta square under root sin z beta cos z. So, this is for ellipse, this can be used for ellipse. So, what is the assumption here? Assumption is that alpha is greater than beta, okay. Provided this is the assumption, we will write here under this assumption this is valid. Similarly, if you have alpha equal to beta, so in that case, so this case will be applicable to parabola. This will be applicable to parabola, and in this case the simple integration is alpha plus beta cos z Okay. That was the case of parabola. Now, we have the case of hyperbola. In the case of hyperbola, the following equation will be applicable, and here alpha is less than beta. So, for this case, you can look into a standard textbook. I am not going to work it this integration particularly here. We lack a lot of we have very short time to finish this course. Okay. So, these are the three cases of integration depending on how alpha and beta they differ from each other. Okay. So, considering the first equation, this one, and from here also we can work out. So, here in this case we assume alpha is greater than beta. So, the case of ellipse, now we are going to just work out. Alpha is greater than beta, alpha is greater than beta. So, if we take alpha outside, okay, and basically what we are interested in, we have to express it in this format. If we are able to do this, our job is done. Okay. So, we write here beta equal to E and alpha equal to 1, where E is less than 1. Okay. So, therefore, this is satisfied, beta will be less than alpha. So, if we do this, so our equation then gets reduced to d theta by 1 plus E cos theta whole square. In this particular equation, beta equal to, we are writing E and alpha equal to 1. So, this is 1 minus E square. So, here we get 1 minus E square to the power 3 by 2. And rest of the things we have to write here, 2 tan inverse alpha equal to 1, beta equal to E. Here in this place we have to insert all those values. So, 1 minus E, 1 plus E under root tan theta by 2, z is replaced by theta here in this case. So, that becomes theta by 2. minus E, this beta is replaced by E. So, E 1 minus E square, z is replaced by theta. So, we get here sin theta and 1 plus E cos theta. And of course, this quantity is t minus t, and we have here also we have the quantity L square by h here present in this case, L square divided by h. So, on this side we have to multiply it by L square divided by h. So, we rearrange this part, just this part we have to rearrange to work it out. So, ultimately we have to express it in terms of m. We bring this quantity on the left hand side, and this will be h times 1 minus E square to the power 3 by 2 divided by L square times t minus t, and on the right hand side then we have this whole quantity to be copied. And this part is simple, h equal to mu times L under root 1 minus E square to the power 3 by 2 divided by L square t minus t. This is LHS. Mu to the power 1 by 2 divided by L to the power 3 by 2, 1 minus E square to the power 3 by 2, and this quantity, as you can see, this is nothing but mu to the power 1 by 2 A to the power 3 by 2, which we can write as, and obviously one term is missing. So, that term also we add. This is t minus t, mu to the power 1 by 2 divided by and we know this quantity is nothing but n t minus t. Okay. Where what information we are using? We have used L equal to A times 1 minus E square and n equal to mu by A cube under root, mu by A cube under root, as we have used earlier. So, this information we are utilizing. So, left hand side then here in this equation gets reduced to m. So, therefore, you get here this m equal to n times t minus t, and on the right hand side then whole thing we have to copy from this place, which is 2 tan inverse 1 plus E 1 minus E under root tan theta by 2 minus E times 1 minus E square times sin theta. So, this expression is for ellipse. The same way, the second equation if we use here, this particular one. So, we get the equation for the parabola. So, if we take alpha equal to beta equal to 1. Okay. So, in this case beta is equal to E equal to 1 for the case of parabola. This case here itself we can write it in short. So, you can see that the and z we replace with theta. So, we can see this here the square is missing, this square we have to put it here, the square is missing. Okay. For the case of here also the square is missing, we have to put the square. Okay. So, if we utilize this, so you can see that this gets reduced to d theta divided by 1 plus cos theta whole square equal to 1 by 2 tan theta by 2 plus 1 by 6 tan to the power q theta by 2. Okay. So, we know once this quantity can be written like this. So, it becomes easy. Therefore, we can take the case of parabola. Okay. So, t minus t equal to L square divided by h, as we have done here, L square divided by h. The rest of the things they appear as 1 by plus e cos theta whole square, and this quantity is known to us. Okay. So, we can utilize it, and if this part we take it on the left hand side. So, that gets reduced to h by L square, this gets reduced to t minus t d theta by 1 plus e cos theta whole square, and we know this quantity is nothing but one more part here. Now, this part we do not write as m, because 1 minus e square was also there. So, we have to take care of that, we simply write it this way, and on the right hand side then we put the whole thing. So, right hand side here in this case will be one by 2 times one by 2 times tan theta by 2 tan theta by 2 plus 1 by 6 times tan to the power q theta by 2. Okay. So, this way we will be able to work out the whole problem. And obviously, the way we want to express h equal to mu times L under root, and therefore, this divided by L square, this will be divided by L square here. So, this becomes mu under root divided by L to the power, and in this case this comes as, and perhaps we have obtained the same equation using the normal integration process earlier. I will just check once. Okay. So, earlier we have written the equation, just I will repeat there. We have written t minus t equal to h q divided by 2 mu square, and then tan theta by 2 plus 1 by 3 tan to the power q theta by 2. So, these two we are now taking it inside. So, this becomes 1 by 2 and this will become 1 by 6. Okay. This is 2 here. So, only part remaining is this thing h cube and mu square. So, if we take it on the left hand side, so that becomes mu square by h cube times t minus t. This is other part. Okay. So, if we try to reduce it, so here in this case we have written in terms of see here this part mu by L cube as we can express, or h by L square, whatever the way we want to express. So, say if we eliminate here in this case let us say we eliminate h. So, it should get reduced to this format. Okay. So, this mu square and h equal to mu times L under root. Okay. So, this becomes 3 by 2 t minus t, and therefore, this becomes mu to the power 1 by 2 and L to the power 3 by 2 times t minus t. So, we get the same term. Okay. So, this is by usual integration process we got, and this we have got by using the standard equation given in the text. So, there is no difference between this either this or that, both way it is the same, but in one case you have to remember the equation, another case you can derive if you know a little bit of the integration process. Okay, so, this way we complete this lecture here and return back to the same issue, that is we are going to write the equation for the ellipse again, because the hyperbola I will take at the end, not right now. So, once we finish this part, we are going to take the case of the hyperbola. So, already we have written the equation for the hyperbola using the standard equation from the your integration textbook. So, thank you very much for listening, and we will continue in the next lecture.